Hi everyone and welcome to today's video. So today we're going to be learning another technique of integrating different numbers. So we've already learned about the substitution method, but today we'll be learning how to integrate using the trigonometric substitution method. Alright, let's learn something new. Alright, so trigonometric substitution it is today. So what I'll call this section is sine, tan or sec trigonometric substitution in integration. So in mathematics, trigonometric substitution is the replacement of trigonometric functions for other expressions. So we use it on numbers where substitution method will not work. So I had shown you a first method. One of the methods you could use for solving most numbers is U substitution or that chain rule of integration. But there may be cases where that method cannot work, and that's where we'll have trigonometric substitution helping out. So as you can see, one of the cases is trigonometric substitutions help us integrate functions with square roots in them. So this will actually also be useful in cases where there are square roots involved. Now obviously trigonometric substitution can also work in cases where there is no root, but in case you have square roots, they will also be useful in that case. So that's what we have. So trigonometric substitution is also appropriate when we have an integrand that is containing the sum or difference of the squares of a constant and a variable. So mark those words: when we have an integrand containing the sum or difference of the squares of a constant and a variable. So three common trigonometric substitutions are the restricted sine, restricted tangent, and restricted secant. So the table below outlines when each substitution is typically used. So look at this. So as you can see, each one of these cases has the difference or the sum of squares of a constant and a variable. So a here represents the constant and here x represents the variable. So now if you have a case where you have a root and then we have the square of a constant minus the square of the variable, in that case we shall make x to be equal to a sine theta. And then if you have another case where we have to find the square root, where we have the square root of the constant, the squared of the constant plus the squared of the variable, or when they're not even in that root but it's the sum of the square of a constant and the sum of the squared of the variable, in that case we use x is equal to a tan theta. So a here represents the constant. And then when we have that case where we have the difference, now we have the square of the variable subtracting the square of the constant inside a root. In that case we make x to be equal to a sec theta. Now all these will make very much sense as we look at different examples. Alright, so to begin with, we're going to look at integration by sine substitution. So as we've seen, if you have an integral of the form, so this one is a case where we have, so this is 1 over, so we have the square root of, now here it is the constant, the square of the constant subtracting the square of the variable. So what happens is, in this case we actually use sine substitution. So if it's actually arranged this way, so what we can do is, if you have this example like this, we factorize out the a squared. So when you factorize out a squared from here, we'll actually see that inside where this a squared was, will remain with a 1, and then we'll have b squared being over a squared inside brackets. So that's what happens when you factorize out an a squared. Now what makes this part true is when I multiply the a squared back in, it will give me this again, and that's how we do it. And then after that we actually extract this a squared value from the square root, and then we have an a, because that 2 cancels with the square root. Then we have a into 1 minus b over ax bracket squared, and that's what we have. So in this case, where the integrand contains a square root of a difference of squares, so in this case where the difference of the squares is the square of the constant subtracting the square of the variable, in that case we use sine substitution. So what we're going to do is we're going to let b, in this case we're going to let b over ax, this value here that you actually see in bracket right here that has a square outside, we're going to let b over ax to be equal to sine theta. As you can see, the reason we put the squared outside is because every single value inside there contains the square. So this is actually okay. So whatever value is inside here is going to be equal to sine theta. So that's basically what you need to remember as we look at the different examples. So example number 1, we're being told to evaluate the integral of, so this is we have the square root of 1 minus x squared dx. So what do we do in this case? We're going to use sine substitution, because we can actually see that we have the constant right here subtracting the square of the variable. So this is actually going to work with sine substitution. So this is what we have right there. So what we're going to do is, by sine substitution, we're going to let x, as you can already see that this is already arranged. We have a 1 on the side of the constant, we actually have a 1 minus, and then on this side we already have we have x being squared. So we're going to let this x value to be equal to sine theta. So what we will do is, when we differentiate this, dx d theta shall be equal to cos theta. And then when we make dx the subject, dx shall be equal to cos theta d theta. So if we solve for theta itself, so that means we're going to go back here. That means we're going to make theta the subject. You can actually see that theta shall be equal to sine inverse of x. So theta shall be equal to sine inverse of x. And then now that we know that, we're going to now substitute everything back right here. So where we have this x, we're going to substitute with it a sine theta. But as you can see, because the x is squared, we have a sine squared theta. So we have 1 minus sine squared theta. And then the dx shall be equal to cos theta d theta, and that's what we substitute right there. So this can be brought to the front, and this is what we end up having. But 1 minus sine squared theta from trigonometry knowledge is equal to cos squared theta. And then because we have the square root of it, it's going to be cos theta. So we have cos theta times cos theta, which is equal to cos squared theta. So now we have to solve for cos squared theta d theta. Now, from the knowledge of even powers of cos theta, we remember that cos squared theta is equal to a half into 1 plus cos 2 theta. So that's a knowledge from trigonometry. So we're going to put that back. So the integral then becomes a half into 1 plus cos 2 theta d theta. So now we can pull out a half from that, and then we're going to integrate these two individual values, the 1 and then the cos 2 theta. So when you integrate the 1 shall become theta, and then cos 2 theta, when you integrate that, it's going to be a half sine 2 theta plus c on the outside. Now, what we're going to do is, we cannot leave it like this. We cannot leave the terms in terms of theta. So we're going to substitute everything back. So now we already know, as we've solved before, we already know what theta shall be equal to. We've said that theta shall be equal to sine inverse of x. That is okay. Now we have to solve for this sine 2 theta and then put it also in terms of x. Now from trigonometry, we know that sine 2 theta is the same as 2 sine theta cos theta. And then we can actually see, we remember that we said that sine theta is equal to x. Now that is the same as sine theta being equal to x over 1, because it being equal to x can also be simplified as x over 1. So we're going to represent this on a right angle triangle where we have an angle theta. So we have an angle theta here, and then as you can see, we remember that sine is opposite over hypotenuse. So that means that the opposite of the angle theta is x, and then the hypotenuse is 1, and that's what we have right there. So now we want to find this other missing part, the adjacent of the angle. So from Pythagoras theorem, we know that a squared plus x squared is equal to 1 squared. Now a is the value we're looking for. So a squared shall be equal to 1 minus x squared, of which a shall be equal to the square root of 1 minus x squared. So now we know the value of the adjacent of the angle. So now with that value, we know that cos theta is actually adjacent over hypotenuse. So we know what the adjacent is. So it's going to be this divided by 1, of which that is basically 1 minus x squared, roots of 1 minus x squared. So we're going to substitute that back in also. So we know that sine theta is x, and then we know that cos theta is square root of 1 minus x squared. So we substitute that back in. But we also remember that theta is equal to sine inverse of x. So now we put all those back in, and this is what we end up having. So now this 2 and this 4 cancel, and then we remain with a half. So a half we multiply in, and this is what we end up having. So we have a half sine inverse of x plus x into 1 minus x squared over 2 plus c. and therefore as our final answer we can actually see that we can extract a half. There is a half in common in both, so extract out a half and we shall have sine inverse of x plus x root of 1 minus x squared plus c, and that is the answer. Alright, so let's look at a question. This is question number 2. So we're being told to find the integral of 1 over the root of 9 minus 4x squared dx. So how do we solve this? So I can already see that we have the constant. As you can see, this 9 is actually a squared, though it may not be clear to some people because 9 is actually 3 squared. So you can actually represent that as a squared. So we have a constant minus a variable squared. A constant minus a squared variable. So this is clearly going to be sine substitution. So what we're going to do is we're going to have that. So now, first of all, we need to make sure that we have it in terms of 1 minus x squared. So what we're going to do is where we have this constant here, we're going to actually factorize it out. So when you factorize it out, we have 9 into 1 minus 4x squared over 9. And then we know that we can also extract this out of the root because this is 3 squared. The square root of 9 is 3. So we extract out that 3 from the root. And then inside we remain with this. But also 4 is equal to 2 squared. And then 9 is equal to 3 squared. So we extract out the squares. And then we remain with 2x over 3 bracket squared. And that's what we have in the most simplified version. So now that we have it in this format, we can actually now introduce the sine substitution. So we can see that by sine substitution, 2x over 3, this value in the bracket shall be equal to sine theta. So when you cross multiply, 2x shall be equal to 3 sine theta, and then if one makes x the subject, x shall be equal to 3 over 2 sine theta. And then when we differentiate that, dx d theta shall be equal to 3 over 2 cos theta. So dx, if we make it the subject, shall be equal to 3 over 2 cos theta d theta. And then let's solve for theta. So theta shall be equal to, so if you look at this, you can actually see that theta shall be equal to sine inverse of 2x over 3. So when you put this back in, we now have 1 over, so remember this 3 right here, so this 3 into 1 minus sine squared theta times 3 over 2 cos theta. As you can already see, this 3 and this 3 cancel, and then we're left with a half. So a half can be extracted out, and then we have cos theta over root of 1 minus sine squared theta. But 1 minus sine squared theta from the knowledge of trigonometry is equal to cos squared theta. But because we have this root, we can actually see that it will become cos theta. So now we have cos theta over cos theta, which is actually equal to 1. So we have a half into the integral of 1 d theta. So when you integrate that, we have theta. So get a half theta plus c. But remember, theta is sine inverse of 2x over 3. So we'll have a half sine inverse of 2x over 3 plus c, and that is the answer. Alright, so move to a question from UNEB 2019, and this was question 12b. So this is going to be our number 3. So we're being told to evaluate the integral of 1 over, so we have an x squared outside multiplying a root 25 minus x squared dx. So this is also going to require sine substitution, as you can already see. So let's first see how to arrange this. So now as you can see, the first thing we can do is we can factorize out the 25, and when we factorize that 25 from here, from this equation 25 minus x squared, we will have in bracket 1 minus x squared over 25. And that's what we have. And then next, we can actually see that 25 is actually 5 squared. So that means we're going to have an x squared over 5 squared. So as you can see, we can group the x over 5, and then we can pull the squared outside. And then at the same time, as you can see, we can actually see that the square root of 25 is 5. So that 5 is going to come out of the root, and then we're going to have it multiplying the x squared, and we'll have 5x squared. So this is what we end up having right there. So now when we have it in this format where it is 1 minus the squares, we can actually now introduce sine substitution. So by sine substitution, we're going to let this value inside the bracket here, we're going to let it be equal to sine theta. So we have, so this is the same as 1 over 5x. So this is exactly that. So 1 over 5x shall be equal to sine theta. So 1 over 5x is the same as x over 5. So it's basically the same thing. So when you cross multiply, we have x being equal to 5 sine theta. And then if we differentiate, we know that dx d theta shall be equal to, so the derivative of sine theta is cos theta. So now that's why we have 5 cos theta. So when we make dx the subject, dx shall be equal to 5 cos theta d theta. So now that we have that, we can now solve for theta. So now solving for theta, we're going to go back right here, and as you can see is we can actually make theta the subject. So what we're going to do is we can actually see that make theta a subject, theta shall be equal to sine inverse of 1 over 5x, and that's how we solve for theta. And now this is a unique example because we have the value x squared right outside there. So what happens there, because we will not have any value that will cancel out with that, but good enough, because we know that x is equal to 5 sine theta from here, we can actually find what x squared is going to represent, because every single value has to be converted into theta. So that's what we're going to do. So we're going to square the x. So when you square the x right here, x squared shall be equal to 5 sine theta in brackets squared. So now that is the same as 25 sine squared theta. So now that we have that, we're going to substitute that where we have the x squared. And now I believe we are ready to substitute everything in. So now this is how our integral is going to become. So dx is going to be 5 cos theta d theta. As you can already see here, where there was x squared, right here, we've actually substituted that with this. So we have 5 multiplying that value. Then inside our root we now have, because we said that that value in bracket is going to be equal to sine theta, so now we have 1 minus sine squared theta. Alright, so that's what's going to be the next thing. But now we also know that 1 minus sine squared theta is the same as cos squared theta. So now when we put that in a root, it's going to be equal to cos theta. So now we have 25 sine squared theta times cos theta right here. As you can see, this value and this cos theta and this cos theta shall cancel. Then we'll be left with 1 over 25 sine squared theta. So now we can pull out the 1 over 25 from that, and then it will actually go out. But now we also know that 1 over sine squared theta is the same as cosec squared theta d theta. And now what we know is, we know definitely from the derivatives of trigonometric equations that now definitely when we integrate cosec squared theta, it shall give us negative cot theta. So now we have 1 over 25 times negative cot theta plus, so it's more adding to the c right there. So now we cannot leave our final answer like this. Now this cot theta has to actually be put in terms of x. So what we know is cot theta is the same as negative cos theta over sine theta. But we know that sine theta is equal to x over 5 from the calculations that we've done before. So now if we know that, we know from the knowledge of trigonometry that if we represent this on a triangle where we have an angle theta, so we have the angle theta right here. So this is a right angle triangle. Remember that sine theta simply means opposite over hypotenuse. So the opposite of this angle theta is going to be equal to x. So x is going to be right here. And then we have the hypotenuse, so the hypotenuse is going to be equal to 5. So we're going to use Pythagoras theorem to find the adjacent value right here, so that we can find what cos theta represents. So from Pythagoras theorem, we know that we have s squared. So s squared is the value on the adjacent, plus x squared shall be equal to 5 squared. So when you make s squared the subject, you have 25 minus x squared, of which a shall be equal to root of 25 minus x squared. And then now that we have that, we now know what the adjacent value shall be. So now that we know that, we can actually now know what cos theta is. Remember cos, so now I have it on a right angle. Remember cos represents adjacent over hypotenuse. So that means cos theta shall be equal to the adjacent, which is root 25 minus x squared, over the hypotenuse, which is 5. So now substituting back for sine theta and cot theta, we can actually see that cot theta is now going to be 25 minus x squared over 5 times 5 over x. So initially it was dividing x over 5, but now when we change this into a multiplication sign, we have 5 over x on the side of sine theta, and that's what we have. So now definitely our cot theta is going to be root of 25 minus x squared over x, because this 5 and this 5 cancel. So now this is what we end up having. Therefore the integral of 1 over x squared over root of 25 minus x squared dx shall be equal to 1 over 25 into negative 25 minus x squared over x plus c. And therefore we can pull this negative out, and therefore this is going to be our final answer. And that's what they wanted. Alright, so now we move on to another question. So this is question number 4. So being told to evaluate the integral of 1 over root of 3 minus x squared dx. Now you can clearly see this is an example of those that actually need sign substitution. So let's solve this. So this is what we have. So as you can see, I can factorize out the 3. So when I factorize out the 3, I have 3 into 1 minus x squared over 3. And then as you can see, I can actually leave it like this. So I end up having root of 3 into 1 minus that. But actually know that 3 is actually the same as the square of root of 3. So that means I can actually convert that into root of 3 squared. So x over root of 3, x squared over root of 3 squared we can combine their powers and we'll have x over root of 3 into bracket, then there will be a squared outside. Knowing that when I put this squared back inside, it will take me back to what I originally have right there. So by sign substitution, I can see that we can let x over root of 3 to be equal to sine theta. And then if we make x a subject, x shall be equal to root of 3 sine theta. Let's differentiate that. Dx theta shall be equal to root of 3 cos theta. And then if we make dx a subject, dx shall be equal to root of 3 cos theta d theta. And then if we solve for theta, and that means we're going to solve it from here. So if we make theta the subject, we shall say that theta shall be equal to sine inverse of x over root of 3. So now therefore that means that this is what we end up having 1. So this becomes 1 over 3 into 1 minus sine squared theta times root of 3 cos theta d theta. So therefore this is what we end up having, but now the square root of cos squared theta is going to be equal to cos theta. So now we are left with root 3 cos theta over root 3 cos theta, of which that shall be equal to 1. So now have the integral of 1, it's going to be equal to theta. So we have theta plus c. But remember that theta is sine inverse of x over root of 3. So therefore our final answer is sine inverse of x over root of 3 plus c, and that is what we are looking for. Alright, so now let's look at another example. So this is question number 5. We're being told to evaluate the integral of 1 over root of 4 minus bracket x minus 1 squared. So now this is a little bit different, but you can actually see that this value inside the bracket here is actually squared. So this is the variable right here is 1x minus 1 bracket squared. And then the 4 is actually 2 squared, and we already know that. So now let's first arrange this properly. So as you can see, we can factorize out the 4 and we'll be left with 1 minus x squared minus 1 bracket squared over 4. But remember that 4 is the same as 2 squared, so that means we have x minus 1 over 2, and then we'll pull out and have the squared on the outside. So we end up having x minus 1 over 2 bracket squared. So also we know that the square root of 4 is 2, so now we pull that 2 outside the root. So this is what we end up having finally. Now we can clearly see that this is the value in bracket here is what we're going to let to be equal to sine theta. So by sign substitution, x minus 1 over 2 shall be equal to sine theta. So if we make to make x a subject, we can see we have x minus 1 being equal to 2 sine theta, and then x shall be equal to 2 sine theta plus 1. So therefore if we differentiate this, dx theta shall be equal to 2 cos theta. Dx theta shall be equal to 2 cos theta d theta if we make dx the subject. Now let's solve for theta. From here, right here, we can actually see that theta shall be equal to be sine inverse of bracket x minus 1 over 2. So therefore, our integral shall be 1 over 2 into bracket 1 minus sine squared theta times 2 cos theta. But now you know that this 1 minus sine squared theta is the same as cos squared theta. And we can already see that this 2 and this 2 shall cancel. So this is what we're left with. Now this shall give us cos theta over cos theta, of which when these divide each other, we're left with 1. So we have integral of 1 d theta, which is equal to theta plus c. But remember, theta is sine inverse of bracket x minus 1 over 2. So our answer shall be sine inverse of bracket x minus 1 over 2 plus c, and that is the answer. Alright, now next we're going to move to a different section. So this is a different group of numbers in sign substitution that require a method called completing the square. Now this is what we're going to look at. Now let's first discuss why we have to complete the square. So why we complete the square? Why complete the square when we can just use quadratic formula to solve quadratic equations? So now completing the square is going to apply to those values that are in quadratic equation form. So sometimes completing the square makes the equation easier to solve. Now that is a key statement that you have to actually understand. So there are times where the form ax squared plus bx plus c may be part of a larger question, and you're rearranging it as a into bracket x plus d squared plus e makes the solution easier because x appears only once. Alright, so in integration right here, we're going to sometimes have to complete the square of some quadratic equations so that they're actually easier to integrate. So this is going to be a key tool that you can have in your hands. Now let's learn how this works. So if you're given a quadratic equation, ax squared plus bx plus c being equal to 0, and then we are being told to turn the quadratic equation into this format, a into x plus d squared plus e is equal to 0. It's actually possible, but all you have to remember that now d shall be equal to b over 2 over a. So now if this is your b, so to get this d value, you get b over 2 times a right here. And then to get e shall be equal to c minus b squared over 4a. So our c value is right here. You get this value minus the squared of b over 4 times this a, and that's how you solve for d and e. So when you substitute that, you'd actually have simplified it by completing squares. So let's look at examples to actually understand this further. So let's see, if you're told to simplify this x squared plus 4x plus 1 by completing squares, how do we do this? So this is what end up having. As you can see, a is equal to 1 because the coefficient in front of x is definitely 1 in this case. Then c is equal to 1 also, and then we can see that b is equal to 4. So by completing squares, we should have a into x plus d squared plus e. Now let's first find d. So remember, d is b over 2a, of which, and then e is equal to c minus b squared over 4a. Now let's substitute that in. So now we're substituting for b over 2a where we actually have a d right here. So as you can see, we now have 4 over 2 times 1, like that. And then where we have a c, we have a 1 minus, then we have 4 squared over 4 times 1. Then we have 1 multiplying this bracket from the outside. So after multiplying and doing all that, we are left with x plus 2 squared plus bracket 1 minus 4, of which this is equal to x plus 2 bracket squared minus 3. And this is what we get after completing the square. So this is the simplified version. So let's look at another example. How about if you are told to simplify 3 minus 2x minus x squared by completing squares? Now in this case, all we have to do is we have to rearrange it so that the variable is starting from the highest power. So this can be rearranged as negative x squared minus 2x plus 3 being equal to 0. So you can see that a is negative 1, b is negative 2, and c is 3. So by completing squares, we should have this, of which d is b over 2a and e is equal to c minus b squared over 4a. So this is what we end up having when we substitute all the values in. So when we simplify this, we have this. Then we'll be left with negative bracket x plus 1 squared plus 3 plus 1, of which this is now going to have, so 3 plus 1 is 4, of which when we rearrange this, we'll have 4 minus bracket x plus 1 squared. And that's how we complete the squares in this case. So now that we know how to complete squares, let's look at integration, where in sine substitution, where we need to complete squares first. So in question number 6, we're being told to evaluate this, to find the integral of 1 over root of 3 minus 2x minus x squared. So let's solve this. So as you can see, we're going to consider that value that is inside the root. So we're going to complete squares for it so it's in a more simplified format. So this can be rearranged as negative x squared minus 2x plus 3. So by completing squares, this is what we end up having. And then we'll substitute in the values, and this is what we have. We'll have a negative 1 into bracket x plus 1 squared plus 3 plus 1, of which this can be rearranged as 4 minus bracket x plus 1 squared. So now that we have this, we can actually now substitute it back in. So now this is now we can clearly see that this number requires sine substitution. So we can actually factorize out the 4. So when we factorize the 4, will be left with 1 minus bracket x plus 1 squared over 4, of which you know that 4 is the same as 2 squared. So we'll have we'll have x plus 1 over 2 bracket squared 1 minus that. And then this 4, the square root of it is 2, so that 2 comes out of this root. So this is what we end up having. So now by sine substitution, we can actually see that this value right here, x plus 1 over 2, shall be equal to sine theta. So if we make so we have x plus 1, if we cross multiply, x plus 1 shall be equal to 2 sine theta, and then if we make x a subject, x shall be equal to 2 sine theta minus 1, of which dx theta shall be equal to 2 cos theta, so that's the derivative of that. And if we make dx a subject, dx shall be equal to 2 cos theta d theta. Then now let's solve for theta. We can actually say that theta shall be equal to sine inverse of x plus 1 over 2. So therefore, our integral becomes 1 over 2 into 1 minus sine squared theta times 2 cos theta. As you can already see, this 2 and this 2 cancel. So that's going to simplify everything. And then we can actually see that 1 minus sine squared theta is the same as cos squared theta. So if we find the square root of this, we'll have cos theta over cos theta, of which that is 1. So the integral of 1 is theta plus c. But remember that theta is sine inverse of x plus 1 over 2, and that is it. So our final shall be equal to sine inverse of bracket x plus 1 over 2 plus c. Alright, let's look at another example. So I'm being told to find the integral of 1 over root of negative 2x squared plus 12x minus 9 dx. So this is another example where we can first complete squares to first simplify that value at the denominator. So now let's consider negative 2x squared plus 12x minus 9. So as you can already see, by completing squares, we'll have negative 2 into x plus bracket 12 over negative 4 bracket squared plus bracket negative 9 minus bracket 12 squared over negative 8, which this is how it will be. And then it will be negative 2 into x minus 1 bracket squared plus 9, which when we arrange this properly, we'll have 9 minus 2 into bracket x minus 3 bracket squared. And that's what we have. Now we can clearly see that this is a number that will require sine substitution. So this is how it will look. So as you can see, the first step we can do is we can actually pull out the 9. So when factorize out the 9, this is what we end up having. Now we know that the square root of 9 is 3, so 3 can come out of the root. And then we know that 9 also represents 3 squared. So we shall have this. So now if we were to include everything right here inside the root, we can actually see that this 2 is also the same as root of 2 times root of 2, so it's the squared of root of 2. So when you put everything under the same squared, the same power, so we shall have root of 2 into x minus 3 over 3, and this is what we have. So now by sine substitution, we can clearly see that root of 2 into x minus 3 bracket over 3 shall be equal to sine theta. So now when we cross multiply, we can clearly see that x minus 3 shall be equal to 3 over root of 2 sine theta, of which x shall be equal to 3 over root of 2 sine theta plus 3. Now dx theta shall be equal to 3 over root of 2 cos theta. Now if we make dx a subject, dx shall be equal to 3 over root of 2 cos theta d theta. So if I solve for theta, I can clearly see that theta shall be equal to sine inverse of root of 2 into x minus 3 over 3. And then if I substitute everything back, this is what I end up having. So now I can clearly see that this 3 and this 3 shall cancel, and then I can clearly see that 1 over a half root of 2 shall be pulled out of the integral. So inside I'll be left with cos theta over root of cos squared theta, of which this shall be equal to cos theta over cos theta, of which now that is 1. So now I'll have a half. So when I integrate that 1, I'll have a half, 1 over root of 2 theta plus c. But remember that theta is equal to sine inverse of root of 2x minus 3 over 3. So when I substitute that back in, this is the answer I have: 1 over root of 2 sine inverse of bracket root of 2 times x minus 3 over 3 close bracket plus c, and this is the answer. Alright, let's look at a question in number 8. So we're being told to find the integral of x plus 3 over root of 7 minus x minus 3 squared. Now this is slightly different because we now have a numerator value that actually has an x value in it. But as usual, let's first deal with the denominator. So 7 minus 6x minus x squared. So this can be rearranged as negative x squared minus 6x plus 7. So by completing squares, this is what we end up having. So we'll be left with 16 minus open bracket, x plus 3, close bracket, squared. So the squared of that bracket. So this is what we end up having. And we can clearly see that this is a number that will actually require sign substitution. So now this is what we end up having. Now I can see I can actually pull out the 16 from that, and then I'll have 16 into 1 minus x plus 3 squared over 16. But now 16 is the same as 4 squared, so I'll have x plus 3 over 4 being squared, and then this 16, the square root of it shall also be equal to 4, and that's what we end up having. Now by sign substitution, I can see that x plus 3 over 4 shall be equal to sine theta. So that's going to be it by sign substitution. Now I can cross multiply, and I'll have x plus 3 being equal to 4 sine theta, and then if I make x a subject, x shall be equal to 4 sine theta minus 3. Now if I differentiate, I have dx theta being equal to 4 cos theta. Make dx a subject, and it shall be equal to 4 cos theta d theta. Let's solve for theta. We can say that theta shall be equal to sine inverse of x plus 3 over 4. Now when we substitute everything back, this is what we end up having. But you remember that x plus 3 shall be equal to 4 sine theta. How did we know that? We can actually clearly see it right here. X plus 3 is equal to 4 sine theta. So that's how that will work. So I can already see that this 4 and this 4 shall cancel in the process, and then this is what I end up having. So there is x plus 3, we replace that with 4 sine theta. And then here I can clearly see that the integral of, the square root of cos squared theta is cos theta. So this cos theta and that shall cancel, so I'll be left with 4 integral of 4 sine theta d theta, of which we know that the integral of sine theta is going to be equal to negative cos theta. So I have negative 4 cos theta plus c. But now I can't leave it that way. We're going to have to find what cos theta represents. So we're going to use this knowledge of right angle triangle, and then we're going to base on what we already know. So we already know that sine theta is equal to x plus 3 over 4. So when you put this in a right angle triangle, you can actually see that sine theta represents opposite over hypotenuse. So the opposite side shall be equal to x plus 3, and then the hypotenuse shall be equal to 4. So now we need to first find this adjacent right here, and we're going to use Pythagoras theorem. So then from Pythagoras theorem, we can see that s squared we shall have s squared plus bracket x plus 3 bracket close it squared being equal to 4 squared. Then if we make s squared the subject, it shall be 16 minus into bracket x plus 3 squared. And then we shall see that a shall be equal to the root of 16 minus into bracket x plus 3, then square that bracket. So therefore that's what we have as the adjacent for this angle right here. So therefore it means cos theta, which is actually adjacent over hypotenuse, shall be equal to this over that. So we have 16 minus x plus 3 squared over 4, the root of that. And then now we can substitute everything back here, and we can say we'll have negative 4 into this right here plus c. But we can say this 4 and this 4 can cancel, and we'll be left with a negative outside, a negative root of 16 into bracket x plus 3 squared plus c, and that will be the answer that we wanted. Alright, let's look at another question. So we're being told to evaluate this one. So we're being told this is 1 over into bracket 1 minus 9x squared times root of 1 minus 9x squared. So what do we do in this case? So therefore this is what we have. As you can see, one of the most important key things here is you can see that these values here are exactly the same. We have 1 minus 9x squared here, and we also have 1 minus 9x squared here. So what does that mean? It means that there is a way of combining them together. Now this right here is the same as 1 minus 9x squared into bracket to the power 1, and then this here is the same as 1 minus 9x squared into bracket to the power a half. So now since the bases are the same, we can actually use a knowledge of indices where we actually add power. So we can add a half to 1 and have the same base. And then what we'll have is the root of 1 over 1 minus 9x squared with the power 3 over 2, which of course is the same as putting this under a root and then having it to the power 3. So it's something exactly like that. And then now next we can actually now see that this value right here, the 9x squared, is the same as 3 squared. 9 is actually 3 squared. So you can actually factorize out the squared, and then leave in bracket 3x squared. Then it will look something like that. So this is actually one that actually will need sign substitution, as you can already see. So by sign substitution, we're going to let 3x be equal to sine theta, and therefore if we make x a subject, x shall be equal to a third sine theta, of which now if we differentiate that, dx theta shall be equal to a third cos theta right there. Then if we make dx a subject, dx shall be equal to a third cos theta d theta. So if we solve for theta and make theta the subject, we shall see that theta shall be equal to sine inverse of 3x, as you can see from right here. So it shall be sine inverse of 3x. Then so therefore if we substitute everything back into the integral right here, we can see that what we have is 1 over the root of 1 minus sine squared theta, bracket that, cube it, times a third cos theta d theta, and that's what we have right there. And therefore we can say that we can factorize out a third, and what we'll be left with is that. So inside here we can actually see that this value here, the root of cos squared theta, is the same as cos theta, but because there's a cubed here, we shall have cos cubed theta. Then next we add cos cubed theta over this, we'll be left with 1 over cos squared theta, of which 1 over cos squared theta is the same as sec squared theta. Then we'll have it as d theta right there. So we remember that the integral of sec squared theta is actually tan theta. So we'll have a third tan theta plus c. But now next we cannot leave it like this, we'll actually have to solve it and simplify this value right here. So you know that tan theta is the same as sine theta over cos theta, but we already know that sine theta is actually equal to 3x, which is the same as 3x over 1. So when we put that on a right angle triangle, we can already see that that means that our opposite is 3x, and then it also means that our hypotenuse is equal to 1 from right here, because SOHCAHTOA shows us that this is opposite over hypotenuse. And then now what we want to find is the cos theta value. So how are we going to do that? From Pythagoras theorem. So Pythagoras theorem, we have a squared plus 3x squared being equal to 1 squared. Then if we make a squared the subject, we'll have it being equal to 1 minus 9x squared. And then therefore a shall be equal to the root of 1 minus 9x squared. So therefore that's going to be the adjacent value. So that means the value of cos theta shall be equal to the root of 1 minus 9x squared over 1. So this is the same as just root of 1 minus 9x squared. So when you substitute that back in right here, this is what we end up having. We end up having 3x times 1 over root of 1 minus 9x squared, which is actually the same as you can already see, this 3 and this 3 shall cancel. Then we'll be left with this x right here at the top. So we'll have x over the root of 1 minus 9x squared plus c, and that's going to be our answer. Alright, so lastly we have a question from UNEB 2001, and this was question 16c. So we're being told to evaluate. So this is actually an example of a definite integral. So it has the limits. The higher limit is 3 and the lower limit is 0. So into the integral of the root of 3 plus x over 3 minus x dx. Now this is quite a little bit different, because you cannot directly see that this is actually a number. It will also require sign substitution. It's because we don't see any value being squared, and we don't see anything like that, and it's because we have everything under the same root. Now when you have such a number, you'll actually have to first rationalize. So rationalizing is going to be the first step. So we're going to rationalize the denominator value. So when you rationalize the denominator value, this is what we end up having. So when you rationalize that, because we actually want to eliminate the root from the numerator, so that we only have it at the denominator. So this is what we end up having. So we'll be left with 3 plus x squared over 9 minus 3x plus 3x minus x squared. So when we solve that, we can actually see that the root of 3 plus x squared, this 2 and this root shall cancel. So at the numerator we no longer have a root, so we'll be left with 3 plus x at the numerator. Now the denominator, we can say at negative 3x plus 3x, these 2 will cancel, then we'll be left with 9 minus x squared over the root. So we're only left with a root in the denominator. So now, as you can already clearly see, that now we can actually directly use sign substitution. So by sign substitution, before we do that, we can actually first factorize out the 9. So if factorize out the 9, we'll be having a 9 into 1 minus x squared over 9. But remember that the root of a 9, the square root of 9 is actually 3. So the 3 comes out of the root. So inside we'll be left with actually, you know that 9 here also is 3 squared, so we can actually pull out that power, so we'll have x over 3 squared, and we'll have something like that. So now we can directly use sine substitution. So by sine substitution, we can actually see that the x over 3 shall be equal to sine theta. So x shall be equal to 3 sine theta if we make x the subject. So if we differentiate that, dx theta shall be equal to 3 cos theta. And then if we make dx the subject, dx shall be equal to 3 cos theta d theta. So if we solve for theta, we shall see that theta shall be equal to sine inverse of x over 3, as you can see from right here, if we make theta the subject. So we shall have the integral of 3 plus x over 3 into 1 minus sine squared theta times 3 cos theta d theta. And then if we make x a subject, we can actually see that actually we'll have to eliminate this x here. But we know that the value of x from here, x is actually equal to 3 sine theta. So when we substitute that back in, we'll also have 3 plus 3 sine theta. So now what happens next is you can actually see that this 3 and this 3 cancel, and then the root of this shall be equal to cos theta. Now you can see that this cos theta and this cos theta cancel. So we'll be left the integral of 3 plus 3 sine theta d theta. And then when we integrate that, we have 3 theta plus 3 into negative cos theta. Now everything, because we have limits, they'll have the limits of 3 and 0. So that's going to be very, very key. Now before we substitute in the limits, we'll actually have to first find what cos theta actually represents. So we put everything in terms of x. But let's first solve for this cos theta. Now we know that sine theta is x plus x over 3. So now they know that we can actually put this in a right angle triangle, and we know that sine represents opposite over hypotenuse, so the opposite value must be x and the hypotenuse value must be equal to 3. So now we can find this adjacent part right here. So from Pythagoras theorem, we can set we have s squared plus x squared being equal to 3 squared. So s squared shall be equal to 9 minus x squared, of which s shall be equal to the root of 9 minus x squared. And then therefore our value for the adjacent shall be equal to root of 9 minus x squared. So therefore it means cos theta, which is actually adjacent over hypotenuse, shall be equal to root of 9 minus x squared over 3. And then therefore we can actually substitute that back, and we'll have this. But we remember that theta also is equal to sine inverse of x over 3. So you can actually clearly see it from here, theta is sine inverse of x over 3. So we substitute all those values back, and then we'll have 3 sine inverse of x over 3 minus 3 into this value right there. So now that we have that, we can actually now plug in the limits. So when we plug in the limits, so we're going to have the group where we've plugged in the upper limit and the group where we're going to plug in the lower limit, and then we'll have the difference of those. Now we can already see that 3 over 3 is actually equal to 1. So we have 3 sine inverse of 1. Then we can actually see it from here that this 3 and this 3 cancel. So right inside here we're left with 9 minus 3 squared, which is actually 9 minus 9. So we have 0 over that. So you can actually see that these values here just cancel. So this is actually unnecessary right here, because they actually just cancel. Now 3 sine inverse of 0 is the other value, but not sine inverse of 0 is 0. So this is actually also off. But now let's go back here. So now this 3 and this 3 cancel, and then we'll have 9 minus 0, which is actually 9. So we have root of 9, which is actually 3. So we're actually left with the root of 9 right here. But there's this minus sign, so we'll have a minus negative root of root 9 from right here. But remember, root of 9 is actually 3. So, but this negative and this negative also combine and they become a positive. So we have 3 sine inverse of 1 plus 3. Now we know from the knowledge of radians that sine inverse of 1 shall be equal to 1.57. So now if we multiply at 1.57 times this 3 right here, we have 4.71. Then 4.71 plus 3 shall be equal to 7.7124, and this is going to be our final answer. So now just remember that in this case we're going to have to substitute, as we're going to have to put our calculator in radians to actually get this answer right here. Alright, so next I have an exercise for you. So I encourage you to evaluate the following integrals using sine substitution. So this is question 1. So we're going to have question 1 up to question 10. Then what I've done is I've put the answers on the right hand side of each question so that you can actually compare with your final answer. So now this will guide you to actually get better in this section of trigonometric substitution using the sine. So this will actually enable you perfect your knowledge of this section. Otherwise, thank you so much for watching. Thank you so much for watching this video. I hope the video really helped you. If you did, feel free to tell me below in the comments. I'll make sure to get time to read through your comments and to reply to you. And also, if you're new to this channel, I encourage you to join the community by subscribing. And then make sure to hit the notification bell so that you get updated every single time I upload a new video. Again, my name is Emmanuel Olega. Thank you so much for watching. See you in my next video.